it's more than enough, okay, and the class is completed. But I am, whatever I am telling now is actually not so important with respect to an exam, but I guess it will be very important with respect to many domains. And maybe, again today I am going to throw jargon circuit. Anyways, so first let's see what is the concept of an auto-encoder. We all have
Shift,
seen
okay, pointer. WASD.
So we all have seen the normal use of a CNN model. See, the basic thing is we have to do AI generated image. The first model which they used was GMM, Gaussian mixture models. Later came this auto-encoder concept, then came variation encoders, then came your what Pratham explained yesterday, GAN, diffusion. What was that? Leonardo AI and stuff where mid-journey, which and all uses diffusion models in order to. Maurya is very great in creating AI-generated images. Just before actually getting into auto-encoder, I think I wanted to tell one line. See, just before starting, one line I wanted to tell you. You know that the proverb in Kannada, Kallana Nambudu, Kullana Nambadu. We have actually one. I actually thought of reframing it as Kallana Nambudu, Kemmavuna Nambadu Anta. Why? Because this topic was given for one person. And that person, Chombu Kodbudru yesterday, they had to come. And the very reason they called me, I don't want to take their name, they know very well. They called me and they were like, how will it test? Sriram, I'm not interested to take the topic, or I'm not feeling well, I won't take the topic. Sriram, full coronavirus, how it looks, I've seen in that one phone call. So this is not my topic to explain. Anyways, so you normal CNN, you use a CNN, you give an image, you make a classification. But for now, for some purposes, let's say.
Just handbrake.
Good.
Good. Thank you. Good. We'll meet you next Monday.
Happy New Year, sir.
Happy New Year.
So bad. I had to close it because it came. This is the one you were playing.
So now let's come to
Never do games.
Before going to generic,
I have
let's speak
this
about
old
reconstructing
midnight
many times because you are all very good photographers also, you might have come across increasing the resolution of your image, converting a black image to a colorful image. There are many such things. Leave AI generating image. Even image, how can you make it better?
It's an old game, so I have to emulate.
And one of the most important technique for that is this auto-encoder, where you give an input image, this image is actually having some distortion.
But it's an old game, bro. You won't play it.
CNN model is reconstructing image.
You don't like it.
Usually you take a CNN model for predicting the class, whether it's a dog or a cat. Now what I'm going to take, this is one CNN model, this is another CNN model. How am I connecting this? What is...
I'm still drawing.
But anyways, so if
I finished the head.
image, it is able to produce a brand new proper image.
That's the part.
No, there is no AI generated image. The bad image is becoming
I will
good.
draw it.
Another
This is just a reference.
image segmentation, especially because he is working on the polyp project, and many people might have seen when there is a tumor, skin cancer detection. I saw their project was there. So if you want to localize, I have given the image of a human. If I want you to segment and give me the mask of the human, I guess auto-encoder is what is being used. Anyways, working of an auto-encoder is what is important. An auto-encoder has an encoder, there's a bottleneck and there's a decoder. These are your CNN layers, everything is your CNN layers. Only thing what I am doing right now is, I will give an image as an input and I will reconstruct an image. I am not doing anything, I am not generating any image. I will give you image, you give me back the same image. This is what right now I am training. Anyways, so now comes what an encoder does is effectively compress the input information. Image, this can be some 1024 plus 1024, some very big image. For a CNN to learn the features, you people would have already known. They would tell start from big CNN filter, as you go, decrease the filter size so that more minute features are being captured in the image. That is what is happening here. Decoder's work is to effectively reconstruct image. This is constructing your image. This is bringing back the new image. One question will come, dumb question. Why Sriram, you are first compressing image, then decompressing image? The most important thing is this middle layer, which I actually want to discuss, because this middle layer is having one superpower. That the power is your encoded information here till here. Remove this bloody encoder just to keep this bottleneck. This bottleneck can actually is having information to decompress an image. Only this CNN layers is more than enough for me to get back the reconstructed image. That is why I am training this model. How Sriram, how is this bottleneck able to having that power is because of latent space. Next, one thing very important, normal CNN you have many loss functions. You have, I think everybody uses binary cross entropy. That is what you do for an image classification task. Very, very important, because yesterday GAN also when you explained, the way you keep your loss function, your entire model only, purpose of your model only will change. Especially when I come to GAN and CGAN, I will tell you how beautifully the entire purpose only changes. You can have many loss function, you can have mean squared error as a loss function between two images itself. You are finding correlation of the image. You can have dice loss. Pardon me, I am not explaining. K divergence, very, very important for my what I am explaining today. Contour loss, perceptual loss, if you had asked ChatGPT, it might tell. Use another image, another deep learning model as a loss. You will be training your own. You people would have learned transfer learning. You will train a big model, then you will train a small model using the big model. This perceptual loss is having a very similar concept. Then you have structural similarity index. You have Navastai loss. This is basically regularization and to imbalance. These are the loss functions. Today clear divergence. Now coming back to the question, Sriram, how is your bottleneck having the power to compress such a big image to some vector? See, the best thing about this bottleneck layer, I don't know, image is actually, it's a matrix. Can you visualize a matrix in a graph? You can visualize a vector in a graph. Can you visualize matrix? At least I have not studied. I can visualize matrix transformation, but I cannot visualize a matrix. An image is a matrix. So what we will do right now is, this bottleneck, I will keep the CNN layer in such a way that it generates me vector. Given an image, I want to represent an image as a vector. This is what my training process is. Now comes what I am going to do with this vector. And this is how an auto-encoder looks. It's exactly same. You will have convolution, you will have max pooling. Here convolution you have no. Here you have a layer called as deconvolution. In TensorFlow or PyTorch, it's called as con transpose, also called as upsampling. Just for your understanding, this is not needed from an exam point of view. This fellow, how many of you remember him? Which semester did he take class for? He has a very important role to play. Actually, I've given a video here to actually understand. I'll tell why Arisha came in between. I need him today for something. This video, you know the vectors. You have 100 images, give 100 images also, generate vectors using the bottleneck. How will that vectors look like? That video I have left other answers video. So basically, I'll send you this video in the group from PPR. What he does is, these vectors, whatever has been generated, he will start plotting it in a graph. Now you might ask question, Sriram, that auto-encoder need not be two-dimensional vector, no, that bottleneck, whatever is there. If I keep this bottleneck to produce two-dimensional vector, that is 2 rows, 1 column, then you can visualize it. If it's an n-dimensional vector, because convolution layer depends on me, I can keep how much ever I want. How will you visualize? How many of you have taken for EL, PCA, ICA, and all for maths EL? Has anyone taken PCA? PCA is a way of compressing. If you want to visualize a 10-dimensional vector in 2-dimensional or 3-dimensional, you can use PCA. That is one way of how he actually uses PCA to imagine the vector. You think it's a 2D vector, as I explained my brain, he starts plotting these points. And this is where the fun part comes. His plotter actually looks like this. So what happens? Eminist, number eminist only, no number eminist. MNS data set he takes number one, only number one images, put number one images, plots as a vector. Take only number 7 images, plot as a vector. What is he plotting? The vector from the bottleneck. First question it should come, why am I studying about bottleneck? What's the use? How is bottleneck related to AI generated images? That comes here. See, bottleneck and AI generated image, now we will be learning little probabilities. And I have to show you some maths. There is some sampling concept which is being involved. But you understood the latent dimension, no? The latent space, the vector, what we are actually doing to get back to vector. This everyone understood, I guess. Now here we have two problems with the latent space. First one is dimension. I told you 2 dimensions. It depends totally upon you how many dimensions you want to represent it. The more number of if you have less number of dimension, that also use that Arvind sir told matrix transformation, and the R power m to R power n you will go. One is gain of information, one is loss of information, and he wrote 2 matrices. So this is again a parameter which you should decide how many dimensions you need based on how much if you're rich or more GPU you can. Anyways, coming to this problem with auto-encoder, you might think, Sriram, you are not still explained only how image is generated, but you have come to a problem. I will tell you why. There is one problem here of overfitting. Oh my god, very beautifully it overfits. And if you take the loss function, if you take SSIM and all as loss function, your loss will never decrease, it will only increase when I drive for high projects. Overfitting comes as a problem. Now, overfitting everybody knows. In linear regression, we know how to tackle overfitting. I showed Harish's photo, if you remember. I had a color photo, it was not looking. Anyways, so I have this M. You people have already derived this in your first semester where he gives y is equal to mx plus c and the one line. And you derive what should be the m value and what should be the c value for. You can derive this. I have time, I will derive. You can derive this, and we add this one term for regularizing constant. What this basically means is prevents overfitting. Sriram linear regression, this prevents overfitting. In auto-encoder, how am I going to prevent overfitting? Point number 1. Point number 2, Sriram, you are still not told how your image is getting generated using an auto-encoder. You only saw reconstruction of an image. There is no new image which is being generated. If I give Yuvraj's photo only will come. I'm not generating it by giving prompt Yuvraj sitting on a throne or something. That is not yet come here. Anyways, these 2 questions, keep it in your mind. Because of this problem with auto-encoder of overfitting, came this new thing called as a variational auto-encoder. Now this actual thing starts. Welcome to variational auto-encoder. Now let's see what happens. So Pratham explained GAN, Sriram explained auto-encoder. Now for generating image, there are 2 ways. First let's speak about generating image problem. You have the bottleneck, no? I told you bottleneck is able to compress all the image into something. So it is having many vectors. Randomly take some vectors, put it inside the decoder and see what image is getting generated. Brilliant idea. It won't work in auto-encoder. Why it won't work? Again, who remembers me explaining KNN in last semester? I explained interclustering, intra-clustering. There is that whole problem with this. Second thing what you can do is, Sriram, instead of randomly taking, you give some dog photo and can you do some kind of a sampling here to generate some other dog photo? That is one way. So in one case, just randomly take some vectors from the bottleneck. In one case, just give a similar image to the encoder. Anyhow, encoder dog image and model वापस encode beko. Dog only it should return back. By doing some sampling here, I will give black dog and can I make it a white dog? This is what I am trying to tell for generating. No racism. Rushin is staring at me. That is one way of doing the image generation. Okay, no problem. Image generation you understood. These are 2 ways of generating images. This is what Sriram had to explain. Oh sorry, I didn't tell the name, no. That was carried on. So next is, this is fine. Vairam, organization of latent space. I told you there is this overfitting problem. How am I written a software? Can you hear it?
No.
Overfitting. One thing got solved was the image generation and we got a clarity. How am I preventing overfitting? For overfitting, See, this you should understand. P of x is the original data distribution. You will have so many images. One question should come. Sriram, you have matrices, images. What do you mean by data distribution of an image? Same question you also asked me yesterday. I seriously don't know actually what it means. What I got it was, this should, if I am training my model to produce images of only dogs, this has to be dogs images. You cannot give cats and billies. That is one thing. That is what is it. Here when we are speaking about the distribution wise, it can be maybe intensity of the pixel, it can be features of the dog, moving in the many such things, but this model can be only one purpose. Though you make it as an AI generated model for dog, it can only generate dog images. You cannot use the same thing for cat. Okay, like for example, so if you keep x, you take some, you have one original distribution P of x. In order to take x as an input, very important, what is the probability P of z given x? P of z is your latent space. Till now we have only dealt about discriminative models. You will give, how many of you remember name base I got? If you give, let's say you have two classes y. Let's say y, one is boy, one is girl, and some set of features I have given x. In name base, if you have seen Mahesh Uttar, you would have done P of y given x, you will find out. What is the probability this individual is a male given these features? P of y given x. What is this same thing? What is the probability that my given input is mapping to this latent space? Because here in an encoder is compressing the image. Given this input, what is the probability it will fall under this latent space? Another thing what I can use, one is you are compressing the information, another way you are even decompressing the information when a decoder is there. That is how you are doing the training procedure itself. Here what happens, now take a vector from z, take some vector, now z is the input. What is, this is probability of x given z. Because here input is x, so I am written given x. Here input is z, so I should put given z. Given this vector, latent vector, what is the probability I will get some image from this x distribution? P of x is your actual distribution, whereas these two things are dependent on theta, your model means and model biases. Sriram, you explained all this fine, but still, there is variation. This is normal auto-encoder, no. There is variational auto-encoder. I told you that is how we are preventing latent space organization. Latent space organization, there are, this was the derivation which you did in first semester. Because Sriram and sir, I have actually written and said this. So how are you going to train them? See, when I am just taking an auto-encoder, I have vectors. Vectors give me some point in the space. Assume I have neuron 1 and neuron 2 in the bottleneck. You can pick how many neurons you want. I have kept 2 neurons. These are points in the data space. 2 problems is already with this. For generating image, I told you will sample some points from here. Assume you have taken some point from here, and though you have taken a point from here, have you trained your model on that point? God knows. Because I know on these points the model has been trained. Some random point if you take, it is in the latent space. But some random point if you take, do you know whether it is trained or not? You don't know. What is this? Point problem of auto-encoder. This is called as PPP. Point problem of perception auto-encoders. Point problem of auto-encoder. So one fellow, I don't know his name, he came across this very good thing, because this is overfitting only, no? You have only fitted to some points in your training data set, remaining points you have left it's overfitting. If you give noise, it is still more worse. I am speaking in a very good case. If your input is having some noise, already hologram people should know. People are using 3D, 3D, something and all, I don't know. Others won't get friends. How will I prevent this overfitting is? Now, right now my model is predicting vector. Instead of making my model predict vector, what if I make my model predict a cluster? Instead of predicting this one vector, I will make this a distribution. By making this a distribution, there is going to be overlapping between many points. Even though I have not trained of some particular point, it is still part of the distribution. So now I have first introduced you to vectors. Vectors are nothing but points. Points are bringing the problem of overfitting. How to reduce overfitting is by introducing this concept of distribution. How will you get a distribution? Again, when you have this model, no? You will have some CNN layers for the encoder. Here you might actually apply max pool or something, and you might get a set of vectors. Question is, how will I make this set of vectors which are points a distribution? Distribution is again you have studied in third semester. What kind of distribution you have studied? Gaussian, Poisson, uniform. I'm sorry, how will you make it a distribution? Distribution will have a cluster of points. Very important. I'm taking one distribution for example. If I take a Gaussian distribution, how can I have to take 2 to 3 Gaussian distribution? Using which parameter can I differentiate this Gaussian distribution from this? Obviously, Arunal sir has again thought, this is one Gaussian distribution. The left side you have, right side you have, standard you have. What is the parameters which you will use for identifying a Gaussian distribution? Exactly, that's what. Thank you. Mean and standard deviation, if you give me, I can identify which cluster it is, where is the origin, I can identify where is the middle, I can identify how much spread it is by using the sigma. So by giving the mu and sigma, I can actually identify which distribution it is. Okay, Sriram, using mu and sigma, you can identify distribution. Model is predicting vector. Think now, model is predicting a vector. I want model to predict a Gaussian distribution. Can I not make the model predict the mu and sigma itself? If it predicts mu and sigma, I know that is the distribution. Correct or wrong? Instead of predicting one point in the distribution, predict mu and sigma will get the entire distribution itself. Understanding, Sriram? That is what I am going to do now. Now what I am going to do is, in auto-encoders, n-dimension input was converted to a less dimension vector. I'll send you the YouTube video, very beautifully he visualizes it using that manual or something only he uses. Here what I am going to do, using an n-dimension input, I'll put it to a Gaussian distribution. You can actually put any distribution which you want. The only reason they specifically chose Gaussian distribution was, I told you input are matrices. And you know that Gaussian distribution can model any kind of a probability. I think he is the best one to explain that, but when he gave that example in class, you people had that question also in exam. Binomial to the he approximates the binomial distribution using the Gaussian, and you remember he converts and does that summation and all. I don't remember, but he actually did it. This is the same thing. That's why we are taking Gaussian, because it can model any probability distribution. Now, instead of my encoder giving me one vector, people who have already worked with auto-encoders, I really think you are able to understand what is bottleneck. I have little worked on, so little I know what it is. Other people, you remember it's just a vector for now. Okay, your encoder is compressing, giving some vector for representing your entire image. Huffman encoding, everybody has done, DSA. You have JPEG compression, many compression techniques. This is also one way of compressing your information. And again, for checking that, you have other, only to check how close this vector is related to your image, you have other loss functions, not getting into that thing. Now I will make it predict mu also, sigma also. Very important, I will do some sampling here. Two ways are there for preventing overfitting. One overfitting was converting that point itself to a distribution. Second way is, from this also I will take some samples only. Got the point? Because the lesser number of samples, the lesser chances of getting overfitting. So I'll be doing sampling here. Now comes one topic called as parameterization. Say, instead of predicting this, I'll be predicting mu and sigma. This is the center of my encoded input. This is one distribution. 1, 1 is one distribution. 2, 1.2 is another distribution. So this whole point, the chapter itself, I converted into distributions. Next, sampling. Now I told you I have to sample some points from this distribution. However, you are given a distribution mu comma sigma. How will you take some point from that? Mu plus 1 sigma, mu plus 2 sigma, mu plus minus 0.1 sigma. If you take, you will get some random points in that Gaussian. Here, instead of doing mu plus some sigma, I am going to do x is equal to mu plus x sigma. This x is going to be taken from 0, 1. 0, 1 is a standard Gaussian distribution centered at the origin, having standard deviation 1. What I will do, from there I will take one point. For that point I will multiply with the sigma of this Gaussian and add the mu of this Gaussian. So it becomes same. Sampling from mu comma sigma is same as sample first from 0, 1. Then you apply this formula. It's very simple. Now sampling one is also done, so I have explained to now how to prevent overfitting also. Welcome to Auto-Encoder. Now comes this problem. So one problem has already got solved. I have converted my points to this one. One thing you should remember, one problem is, if you give only number, you are training, let's say, instead of giving only dog, let's say in the dog also you have breed, no? Road breed, home breed, many breeds you have. Supposing those breeds itself, I am putting one road breed here, home. Is there any formal term for that, or is it fine? Sadak kutta, Toda kutta, something you have. Street dogs and homely dogs, let's keep it. So, you think I am training my model to, Pratham doesn't like dogs, let's put it to cats. Street cats and home cats. So, I am making my model generate street cats, home cats. Street cats are here, home cats are here. Street cats the problem. Now the point has become distribution, problem got solved. Again one problem comes. To generate an image, what did I tell you? You will take some random point from here and give it to the decoder. Sriram, in the middle there is this empty space. No, this is street cat, this is home cat. This middle thing, how will you solve? What if I take some point from here and start generating the image? How can we solve this point? Because within a class the problem is solved. Inside this class you take the point and give the decoder, you will talk again. If you put from here street, you will get street cat only, from here you will get home cat only. In middle if you take something, what will you get? Don't know. You should see the images of, he showed yesterday, you know, with the cat with 5 eyes, dog with 4 tails. One way of actually doing this is, right now if you see, I want to make this compact. How to make this compact is so I have to, this is the class right now, I have first changed it from points to distribution. From a simple distribution, I want to make it a compact distribution. Even now when I club these classes, street cat should be street cat only, home cat should be home cat only. But I should bring them closer. So that this empty space, nobody should take something from this point from this empty space. How am I going to do that? So that we can overlap different classes, so that we can sample points between different classes as well. That is okay, that's what I told. How to solve this inter-class continuity? 2 points are given. What kind of an error will you take for estimating how far they are from each other? Mean square error. Even 2 points, so to mean square error only, you need to find out how much far they are. KL divergence is something which will tell you how, just like how mean square error will tell 2 points how much far they are from each other. KL divergence will tell you how much far 2 distributions are from each other. Remember, I am speaking about mu sigma, I am speaking about a Gaussian distribution. Okay, Sriram, now using KL divergence, you will tell, I told you can solve that problem. My input is my distribution, which I got as a vector mu, sigma, many vectors. What will be the desired output? The desired output is higher enough input. The song was in the previous page. Anyways, the normal distribution, what I'm going to do is, I want to make every distribution come to the middle, mean centered, and I centered, make the standard deviation 1. Who is that distribution? That is nothing but your standard normal distribution. So apply KL divergence laws on your model's distribution. You got a vector, you remember here 1, 2, 3, here 1.1, 1.2, mu, sigma. Take each distribution you take, compare what is the loss or what is the difference between your distribution and the standard normal distribution. By doing this, you can achieve one thing. Niranjan, I have told, I will show Niranjan here. So one this thing I already told. This is a very good article in Medium. I learned many things from there. Second thing is, this is the article. I'll send it in the group if you need. What we require is this. What we get using a variation auto-encoder might be like that. This is your KL divergence. There is a YouTube video for 4 minutes. If you see that, you will understand. You will understand decision tree algorithm entropy is there. No? What is entropy? What is information gain? What is KL divergence? Everything together in 4 minutes is explained. You can see that you are not needed for your syllabus. By applying this, what I have done, I think, I don't know if it's visible there. You are bringing all the distribution more and more closer. At the same time, you are also, this is actually a very big dimension. He has a Papa applied PCA, TSNE and something else for showing this in a 2-dimensional representation. That is why it's looking all jumble. But it's actually very compact, point number 1. Now if you take anything from here, take any point from here, do you think there will be any problem? No. You can take any point from here, put it in my, don't tell Sriram empty space in the I will take. You can take actually. But now if I take anywhere, if I sample any point, this is your bottleneck by the way. If you sample any point and give it to the decoder, do you think there will be any problem? No. Because point number 1, points are converted to distribution. Point number 2, different distributions have become more closer together. Variation auto-encoder, case study. So, in case of variation auto-encoder, KLD is error between your whatever you got meaning what I am trying to tell is this. Your model is predicting this. No, this is one distribution, this is one distribution, this is one distribution. On each distribution, you apply the KL divergence. Basically, find how far it is from the Gaussian thing. You will finish. I think yes. So KL divergence is there is one PyTorch implementation also. I am not writing for you people. Two kinds of errors are there now. So 3 things what auto-encoder changed is point number 1, intra-clustering. Again and again I am repeating this because when I asked ChatGPT difference between CAN and BAE and all, this point is only become one is converting points to the generations to maintain intra-cluster. Within cluster problem, sampling the points is solved. Next is inter-cluster, bringing all the clusters compact by using KL divergence is solved. Point number 3, I told you one problem of overfitting in auto-encoder. Very nicely he has solved overfitting in many ways. Point number 1 by implementing nu comma sigma. Point number 2 by implementing sampling within the model. You have never learned any model where inside the model itself sampling happens. Until yesterday because you explained that yesterday. You saw sampling. And point number 3, by luck, this KL divergence which he was using for bringing it compact, this has another name called as a KLD regularizer. Basically, this also stops overfitting, but how this is stopping overfitting, I didn't understand. That's for you people to left out. I don't know if, yeah. So actually what video I wanted to show here was
very warm welcome to this sound classification.
so this is
So the information is basically
see, supposing I am Ambaran sir and I told you to cheat, I I am a teacher and I told you, see, you come to my mental course, I want you to ask one doubt. I'll tell you this doubt you should ask. Implanting questions. I'll tell you, ask me this doubt. You will come in the video and tell, so I have this doubt. Our Anna will come now. You see, no, I'm saying only. I'm telling, say, one question you should ask, say, go stand on the camera, ask this question. You can remember the question, you can go and ask the question. No, so this is my question. Impact attention, you see.
Okay, the next question is basis and dimensionality impacting the performance of machine learning models.
So basically, why specifically this video I put was point number 1, I got this video from someone, I wanted to show it. Point number 2, he is also asking that question there about how this dimensional, though you are reducing the dimension, that is what you are basically doing, compressing the image, how my deep learning model is able to sit and explore it on your own. I am not telling you. Because again comes here the topic of, you people have all studied perceptron convergence theorem. I asked to say what is perceptron convergence and I understood how well you studied. But there is also something called as auto-encoder convergence. I told you, you give an image, it will reconstruct an image. How can you tell Sriram so 100% that it will reconstruct a given image only? Is by using auto-encoder convergence theorem, which is not there in the syllabus. Move forward, next program. I'm going to finish the class in 5 minutes. So, please. Already Pratham explained yesterday about how a GAN will work. I don't care about the one thing. You know one thing. Just before moving to GAN, I want you to understand what and all I have done. What is an autoencoder? What are the different loss functions? What is the limitation of an autoencoder? Limitation is one I told you, this vector space organization, the clustering, that itself is a problem in autoencoder, and second one is overfitting. Given a noise, it will overfit on the noise also. Why will it overfit? Sit and study, there is a theory, I am not going very further. This much itself is more. So because of these two problems, I told you variational autoencoder came, where he introduced this concept of sampling. I told you there are two ways of sampling. Then I told you what distribution should I use. So we told you sigma, Gaussian. You can use any distribution. You do and check. I don't care. Reparameterization is one technique for sampling. That's what I told. Instead of taking from u comma sigma you point, take from 0 comma 1. This is, and you add sigma multiply, sorry, add mu multiplied by sigma. That is that name they have given us reparameterization. But people who has brain also can understand this. You know that thing is, research paper in an essay or paper, something I should show novelty, reparameterization. KL divergence I told you, now let's go to actually working of a GAN. I am not going to teach full quality. See him against KL. When he will get this minus more of a reward from his course. This is what is very important for me. Yesterday he did this. Only this one thing I will give you. This is your generator, this is your discriminator. One thing, yesterday Pratham explained so much. So for generating an image using GAN, what is the input you get? What is an input? What is the input? GAN generates model, no. So image, no. You have seen text to image. What is the input for this? Random noise. Now question should pakka come in your mind. Text to image means one logic is there. I will tell generate the image of the dog, model will know okay dog. That is again this problem with, this is called as vanilla GAN, the base model of GAN. The one problem here is you cannot refine your input. Now if I tell generate an image of Sriram sitting in every class in first semester, it cannot. Until and unless I train it on only Sriram, only then it will be able to produce, or else no. Anyways, so we are going to give random noise. Point number 1 is Z is your input. Please, for my sake, I cannot agree that by my brain it has become like Y is output, Z is output, X is input. Here, I am good fellow, bad fellow, he has actually taken Z as a term. Z is something you have taken from your real world distribution, which I am representing. This symbol only means Z is sampled from P Z of Z. When you train a model, you will take some random row and train your model. No, that is nothing but you are doing one sampling for training. Again, you people are intelligent to know gradient descent, stochastic gradient descent. This is very similar to it. You are sampling from there. Sampling from there, give that sample. Another one thing, this Z need not be an image. This is my whole fundamental for next conditional gap. This Z need not be an image, it can be any vector. Because I told you, take this vector, feed this to the generator. Generator will give you G of Z. Z is input, you should Z is the input, you will get G of Z as the output. G of Z is nothing but this itself is from a distribution. You have a real distribution, your model will make its own distribution. No, based on your weights, not my weight, the model weight. So based on whatever input is given, model will train its weights and makes its own distribution. So this PG of Z will refer to the model's distribution, the way model has represented your environment. Next thing, very important to understand. When a discriminator is given, point number 1, you are given random goods. Any thing you take, you will always have labeled data set. You will give some meaningful input. You will make it friend propagate. You will find the loss. You are given random noise as input. What will be the output? Expected output. Is it random noise? No. I wanted to generate an image. To generate an image, I should also feed it a real image. Very important thing to understand here is, this training is not a one-way training. And first of all, your discriminator is a simple classifier. Point number 1. Point number 2, this diagram is very deceptive. Why? Because first time what I thought both the input are going at a time. Real image and fake image are going at a time and I thought. But that is not the case. Your training itself happens in 2 phases. First I will train the discriminator to tell, I will give you real image, you should predict me real image. Second training, what I will do, I will give it fake image and I will try to tell that it is a fake image. Correct, no, Pratham? Because 2-stage training, I was not going this way, both are given together. Point number 1. Point number 2, what you should remember here is, first, I told you this is just a classifier. Given real image, it should produce real output. It should produce y is equal to 1, which means it's real. Y equal to 0 and it is fake. Please remember this, y equal to 1 and y equal to 0. This itself will be a problem next. This 1 and 0 itself is not headache. You will be applying sigmoid, you will get 1 and 0. Very important, it's just classifying. And for a classifier, for an image classifier, what is the loss function you use? Exactly. Tejas, no, if he removes the mask, I can hear him much more louder. But COVID people are sitting that side only. Anyways, I am going to use binary cross entropy itself. That will be my first stage of training. First stage, given you a real image, give me real output. The second one, I know you are stupid, I will finish it off. Given a fake image, you should give it as 0. Fake image is generated by using generator. This much everybody understood. Problem, remember the 0 and 1. This itself is going to be a problem. Random noise itself, again that will be another problem. Let's see. And then I am just derived for my understanding, not explaining. One thing what I can explain is, see, this loss function everybody can find out. One thing, who is generating output in a GAN? Only the discriminator. So loss function is going to be associated at which? At a discriminator. This case 1 is when you do the first stage of training. Given a real image, predict it is equal to 1. Only generator only has not come. Apply your simple BCE, binary cross entropy, you will get one loss function. Next, when you give a fake image, the g of x, because fake image is generated from the generator. X is the input means it will be g of x as output. Z is the input and g of z. That is your generator's work. You will write another one cross entropy because this is the second stage. First is real, one second one is this. Very simple question. Normally loss function and you will try to reduce the loss, no? Here what will you do? This is a discriminator and my goal is given a fake image, the discriminator should tell it is real. Then only know that our model has become successful. Eshte tappa kotru obba correct anta andre in Kannada we had, sorry, in Hindi we had that. Some people, you know, you tell them the bad thing also, they will tell, acha, very nice. You tell, you know, tomorrow from best 13th floor I am standing, very nice. Anyways, people who know Pens, I guess, understood the context. Anyways, here do you think I should reduce the loss of the discriminator?
Don't do that, we'll do it.
You should not reduce the loss of the discriminator. Your whole goal is to maximize the loss. The more mistakes the discriminator is making, it means the more better your generator is generating an image. That's why I have put max. Simple. These are not two different loss functions. You can just add them. Case 1, case 2, permutationally cases under you will add. I hope you will remember when to add, when to multiply. I don't. Add, you will get, you have to maximize this. And as Pratham told yesterday only, you have to maximize this. If you have to, I'll just draw the graph. If you have to maximize this, d of x has to tend to 1. If you have to maximize this term, d of g of z, that has to tend to, this also should tend to 1, no? Yeah, d of g of z also should tend to 1. Because only when it is tending, it should tend to 0, correct. Because you have to maximize both. In this function, maximum is a d of x is equal to 1. For this function, d of g of z is equal to 0 makes it maximum. After this, generator must produce very realistic image. This is from the discriminator's perspective. Both I have to maximize. I have given both also. D of x has to tend to 1. My final goal. D of g of z should tend to 0. Discriminator ka work. Come to generator, it should produce very realistic image. If it is producing very realistic image, D of g of z has to tend to 1. Discriminator is making it tend to 0 to maximize this term. But generator has to make this D of g of z go towards 1. Why it has to tend to 1? Because fake image, this is fake image. Fake image tending to 1 means discriminator should tell it is real. That is the meaning of this line. Then will discriminator give d of g of z 1 when it is going to the minimum. That is what we substitute in the formula. Go through this. He has made 150 MB. You know that PDF is. In Word he sends, computer networks he sends 45 and more. If he sends 45 MB, this 150 MB he has sent. Don't compress also. Anyways, this finishes. Coming to the two last things. So now that I told you, in GAN we had 3 problems which he told yesterday. Mortholog's problem, not going into that again. Then we told what was that other? Counting the dog eyes problem. 2 more are there. Which one? Vanishing gradient, and I think overfitting. Overfitting was there. Okay. You know, I have written it up. Vanishing shading, more cards, yes. How to solve these problems? Nash equilibrium. That is one very good thing. See, just now I showed you the graph. Discriminator is telling you tend to 0. Generator is telling you tend to 1. To find that equilibrium, if you have done Nepal course in economics, having Nash equilibrium, that is not even related to this. I don't know why he thought. Simply I joined that course. Anyways, in a vanilla GAN, what we are trying to do is minimize distance between real and generated image. Seeing our loss function, you can actually understand binary cross entropy deals with probabilities. And what are we trying to do there? We are dealing with probabilities. What this fellow, W-GAN, Wasserstein GAN, this is also known as earth mover distance. God knows he is not moving earth also. Minimize the distance between distribution of real and generated image. Because till now I was telling you, that loss function which we derived, that was only for one image or one point. Then he introduces yesterday expectation value he introduces so that he clubs all the points. Even there the problem is we are still dealing with points. We are not dealing with distributions. So what he does, he brings this concept of minimizing distance between distribution rather than probability. Why probability? I am specifically mentioning probabilities because sigmoid is going to give you output from 0 to 1. I told you that itself is a problem. Why? Because it's basically like you are only trying to go to 2 points. Either go to 0 or go to 1. It's like point wise. Again, that is nothing but in logistic regression you are finding the line. You are only either pushing it to 0, pushing it to 1. So what idea he thinks is, instead of using this sigmoid as an output, he is going to use ReLU or linear, no output, no activation itself. This time what will happen, the discriminator is going to be called as a critic. Why? In 5 star, your 2 star image, your image whatever you have produced is 10, means it is very good. If discriminator is giving -10, it means your image, what fake image you have produced is very bad. This way of a regression kind of an output he brings, point number 1. Point number 2 I told you is because when you give 0 or 1 as an output, we are dealing with points. By bringing this entire real number line, now we can deal with the distribution. And when you come to distribution, the last function I told you was KL divergence. KL divergence, they used, didn't work out, they used JS, Jensen-Shannon distance, and the another one metric other than KL divergence. Finally, he came to this Wasserstein thing, Wasserstein laws, very simple only that is also. What Wasserstein laws does is maximize the difference between output on real instances and output on fake instances. Output on real instance is nothing but d of x. Output on real instance, fake, real is d of x. Give a real image x, output will be d of x. For fake, what will be the output? D of fake image. Fake image, how do we get? G of z. D of G of z. Very simple, he tells, for the discriminator, you keep this as the loss function and maximize this. If this tends to positive, which means D of x is good, this D of G of z has become less. What he tries to tell is, as and when you are keeping on increasing this one particular term, you will be getting more and more positive numbers, positive output. From a general, because that is what the negative numbers if you get, you are not doing well. Positive numbers, if he is giving as an output, it means you are doing better. So maximize this. Maximize real image minus fake image. The better and better the value is, it means the model is performing better. You will not have this Nash equilibrium problem because in this time both he uses max only. Maximum, actually you will have a Nash equilibrium problem, not because in the minus and the pluses, we are not going into that. For a generator, maximize discriminator's output for its fake instances. Obviously for a generator, this value has to be maximized. If this value, the D of Z is maximized, what does it mean? It means that your generator is it's giving good feedback. Now generator is not telling that no, this is wrong, this is correct. Now generator's work is to tell this is 10 points better, this is 20 points better. That is why they are trying to maximize this term. In order to deal with vanishing gradients, now this is the total loss function, just add both. You are basically doing max on both. I know I'm going faster. Anyways. Now for this, what is this? Vanishing gradient problem. 2 times training is happening. See, 1 time training if you do only vanishing gradient problem will come. Here 2 times training is happening, 100% vanishing gradient will come. They use this concept called as Lipschitz continuity constant. Don't have in the syllabus, just to show that I have read YouTube, I am putting it here. No need of remembering, but this is one way of solving the overfitting problem. Second, so one problem I told you is instead of making it to 0 or 1, that is sigmoid, I will be making it linear. In order to, instead of discriminate, give it a feedback. Because if you discriminate, you know. It's a reverse, I guess, confusion that was. Conditional GAN, very simple. This time, conditional GAN, instead of giving it a random noise as an input, give a label also. It is like you think you have a Gaussian distribution of only dogs. Take one vector from that and also give the label that this is a dog. Give this label and input for both discriminator and for generator. So your model will try to understand, oh, mean distribution in the, if I get an input, it should be mapped to dog. From this distribution, if I get an input, it should be mapped to cat. This time, I told last time, no, in vanilla GAN, you will only be training on Srikumar's images, but here, You can train on anybody's images, even the label is also present.